Is the universe a hologram? Perhaps you have heard it said that the universe could be a hologram. It is a strange statement, almost science fiction. And yet, behind this claim, there is something that has a theoretical foundation, an idea that could represent one of the most interesting hypotheses developed by theoretical physics in recent decades. Everything originates from the study of black holes and from a paradox that, for a long time, has continued to challenge physicists. But in what sense could the universe be a hologram? What do black holes have to do with it? And above all, how much of this is actually true? Let us try to understand it. The first step is to understand what a hologram really is, because there is often a lot of confusion about this topic. Sometimes people speak of a hologram as a simple optical illusion. For example, the projections used in some shows or concerts, where, thanks to screens, smoke, and light effects, the impression of something three-dimensional is created. Technically, however, these are not true holograms. A true hologram is a three-dimensional image constructed from information that is actually completely two-dimensional. In other words, one starts from a flat surface, like that of a photograph, from which it is possible to reconstruct a complete three-dimensional object. If you have ever seen a real hologram, you may have noticed that it gives the impression of looking through a window. By changing the point of view or the lighting, new information about the represented object emerges. One can move and observe parts of the object that were not visible before. In a certain sense, all the information about the third dimension is completely contained in the surface. The holographic principle in physics arises precisely from an intuition of this kind. The idea is that our universe, the three-dimensional space we inhabit, could in reality emerge from something more fundamental that has one dimension less. To understand where this idea comes from, we must observe extremely mysterious objects, black holes. A black hole is a region of space from which nothing can escape, not even light. Everything that crosses the surface of a black hole, called the event horizon, can no longer return, and is, in a certain sense, lost forever. And it is precisely here that a fundamental problem arises. Physics, and in particular quantum mechanics, tells us that information cannot be completely destroyed. Every physical system contains information: the position of particles, their velocity, their state. This information cannot be lost because the fundamental laws of physics are reversible. In principle, even if not in practice, we could go back in time and reconstruct the initial state of a system starting from the information available today. And here is the paradox. The information that falls into a black hole seems to be lost forever. This problem is known as the information paradox. The situation becomes even more complicated when Stephen Hawking showed, at least theoretically, that black holes can evaporate over time. A black hole that contains information could, in the end, disappear completely. According to Hawking, at the end of the evaporation, only energy would remain, without any trace of the original information. This represents a deep problem for physics, because it violates the principle according to which information cannot be destroyed. In the 1970s, the physicist Jacob Bekenstein began studying the entropy of black holes. Entropy is a physical quantity that, in some way, measures the energy available to do work, and it is often associated with the degree of disorder of a system. A disordered system can be obtained in many different ways at the microscopic level, while an ordered system can be obtained only in a few specific ways. For this reason, a disordered system has high entropy, whereas an ordered system has lower entropy. There is also an interpretation of entropy related to information. A disordered system requires a lot of information to be described, while an ordered system requires less. Bekenstein discovered something surprising. Contrary to what happens for ordinary objects, the information contained in a black hole is not proportional to its volume. It is proportional to its surface. More precisely, the entropy of a black hole is proportional to the area of the event horizon. This result is shocking. All the information contained in a black hole seems to be encoded on its surface, not in its volume. Starting from this intuition, Gerard 't Hooft and Leonard Susskind proposed an even more radical idea. Perhaps this property is not exclusive to black holes. Perhaps it represents a fundamental characteristic of reality. According to this view, the information that falls into a black hole is not destroyed and does not really end up inside it. It remains encoded on its surface. From the outside, everything we can know about a black hole is contained in the two dimensions of its surface. And this is where the analogy with the hologram is born. Just as in a hologram, all three-dimensional information is encoded on a two-dimensional surface. In the same way, the three-dimensional information of a black hole would be encoded on the event horizon. If this principle were general, then even the three-dimensional space we observe could emerge from a more fundamental two-dimensional structure. In this scenario, the three-dimensional universe would be the manifestation of information encoded on a surface with one fewer dimension. This idea is known as the holographic principle. In the 1990s, the physicist Juan Maldacena showed that, at least from a mathematical point of view, it is possible to construct coherent models of this kind. His result, known as the ADS-CFT correspondence, shows a complete equivalence between a theory that describes a three-dimensional space and a theory that uses one fewer dimension. The fundamental question remains open. Does this principle really apply to our universe? As far as we know, our universe does not possess the curvature required by these models. At present, there is no experimental evidence showing that the holographic principle applies directly to the universe we observe. This does not mean that we live in a simulation or that reality is an illusion. Physics has not demonstrated any of this. However, the idea that three-dimensional space could emerge from two-dimensional information remains one of the most fascinating hypotheses of modern physics. If it were true, understanding it could help us better understand space, time, and perhaps the very nature of reality.